I also want to fold it a little bit. I don't want to. Yes, thank you. Is it on? Thank you. Two more minutes. Let's wait for him to come. You can call them to start recording. They started recording. I said, I'll wait for you to come. They stopped the recording. Oh, okay. So that's fine. That's fine. Sit down. It's not, there's still one more minute. Hi, Maithili. You know Dr. Maithili? Meet Professor Maithili. This is Govindan Kutty. He is the organizer for this conference. She is an applied mathematician. Oh. All her life in Institute of Science and TFR. Oh. And she is an emeritus visiting faculty here. I know her for a long time. Okay. Yeah. Welcome back. So, we have a static deterministic model. We derived the model equation from basic physics. We combined the observation with the model. We computed the error, which is the function of the unknown parameter x. Error is a vector. Now let's talk about why we converted error into a scalar. Error has multiple components. So one way to talk about is minimize the individual components, or collectively minimize a function of all the components put together. So in optimization, there are two types of optimization. One is called the uni-objective optimization. Another is called multi-objective optimization. In a uni-objective optimization, there is only one criteria. In a multi-objective optimization, there are multiple criteria. Let me give an example of a multi-criterion optimization problem. An automobile. Every engineering gadget is the design of it is a multi-objective criterion. So what are the criteria in design of a car? I want it to look good. I want it to be cheap. I want it to be safe under 60 miles an hour. Are you with me? I want it to give a large mileage per liter of gas. To give large mileage over gas, liter of gas, it must be light. If it is light, we go to Surga when there is a crash. Safety is forgotten. So safety and gas mileage, they are opposite of each other. So in a multi-objective criterion, I want my ride to be smooth. So when you go into a ditch, oh, the guy who's sitting at the back, oh gosh, I lost my back, right? So I want my ride to be smooth. I want the car to be safe. I want the car to be cheap. I want the car to look good. I want the car to be able to give larger kilometers per liter of petrol. If you want to design a car for each one of these, you won't get a design. The design space is an empty space. So what do the automobile engineers do? They take a compromise. In this car, if you travel at 30 kilometers per hour, if you get involved at a speed of, let us say 25, 30 kilometers, and if you wore seat belt, you may get hurt, but you will not die. It's going to give you 15 kilometers per liter of gasoline. The look is pretty good. I want AC, I want everything automatic, and so on and so forth. Now, can you imagine the designer's goal to be able to achieve not every one of them, but part of everything? That's life, compromise, right? That's right, that's right. That's called multi-objective optimization. Here is a uni-objective optimization. I don't want you to confuse multi-objective versus uni-objective from univariate and multivariate. In a univariate, there is one objective function of one variable. In a multivariate optimization, there is one objective function as a function of many variables. Here, there are many variables and there are many objective functions. Multi-objective optimization is more difficult. So if you thought your job is difficult, talk to an automobile engineer, then you'll feel much more comfortable. You have to just deal with only one criteria, a house builder. I want the house to be cheap. I want the house to look good. I want to have the largest amount of space. I want it cheap. I want to have all amenities. What is me? Every design in engineering is a multi-objective optimization problem. Fortunately, in data assimilation, we have a unique objective, uni-objective optimization. All of you? Every engineering problem, I want you to think about how do engineers solve that problem. So I have a single objective, which is the sum of the squared errors. We expanded that, and we used the rules from linear algebra to get that function into this form. We calculated the gradient, and we equated the gradient to 0, and this is where we stopped towards the end of the last class. And this is where I need to begin. Are there any questions on these? Yeah. Louder. I have. The gradient must be 0 is a necessary condition for a point to be minimum. Did you see this? That's right.
We are putting it to 0.
Right?
It did not become 0.
You had to force it to 0. That's right. That's what calculus tells you, right? The first derivative must vanish. The second derivative, if it is a minimization, is a bowl. If it's a maximization, is a bowl inverse. And how that relates to the curvature of the surface. The positive curvature is the minimum, negative curvature is the maximum. The positive curvature is characterized by the Hessian being positive definite. The negative curvature is being the Hessian being negative definite, the opposite of that. And you should also know the following. Minimum of f of x must be equal to maximum of minus f of x. And that should be easy for you to be able to think. Minimum, I have a parabola. Maximum, just simply invert it. So quadratic function is used in economics for profit function. Quadratic function is used to be able to capture loss in engineering, the cost function. Minimum, maximum. The minimum of one function is the maximum of the negative of the same function. So you don't have to talk about minimizing, maximizing. It is enough to talk about one. All of you? Any other discussion? So what are we going to do? We are going to fall back on the principles of multivariate calculus. Multivariate calculus tells you at the minimum the gradient must vanish. The second derivative matrix Hessian must be positive definite, is already symmetric. So I'm going to force these two conditions. And that's what we are going to start with from here. So let me erase the things that I don't want. So we know how I derived all these things. So let's so if I equate this to 0, this is negative sign, kick it to the other side. 2 will get cancelled. If I equate it to 0, so I get a linear equation, H transpose H, X is equal to H transpose Z. And we have already seen this matrix is a symmetric matrix. How do you test a matrix, a symmetric matrix? The transpose must be equal to itself. Now, what else I want? I want this to be positive definite. I have not proven it is positive definite. I have not examined the conditions under which it is positive definite. Hold on, we will do one by one. Okay, now let's look at this matrix once more. H transpose H. H is a m by n matrix. This is the transpose n by n matrix. So this belongs to n by n. Same thing, H transpose Z. Z is m by 1. This is n by m. So this also belongs to Rn. So this equation is a linear equation in Rn. How many of you are with me? Come on, guys, nod your head. This way or that way. So you can think of this to be Ax is equal to B, where A is H transpose H, B is H transpose Z. Now, I know A, I know B, I want to be able to solve for X. So what is that we have reduced the problem to? We have reduced the problem to one of solving a system of linear simultaneous equation where the matrix of the equation is a symmetric and positive definite matrix. You remember for the two variable problem which I gave you a homework problem, we got two equations and two unknowns. That's a homework. I want you to do that. Please do. Please do. That's how you can relate to things. That's how you can relate to things. Now, before I go further, I want to talk about the second derivative. I want all of you to say hello to my colleague and friend, Dr. Maithili. Hey, raise your hand. Let them know. That's right. She's a colleague. She's a PhD in applied mathematics from Indian Institute of Science. We come from the same school, and I have been friends with her for decades now. She's a control theorist, partial differential equation, data assimilation, and she's in many related areas of activity. Welcome. Glad to have you. Glad to have you. Now, the second derivative is the first derivative of the first derivative. Are you with me? So I already have the first derivative in this equation. So if I took the first derivative of this, the first derivative of this term is 0. Everybody, this is a linear term. All of it with me? So what is this? This is Ax. I have to compute the first derivative of Ax with respect to x. That's a claim. So the gradient of A of x, in that case, it becomes a matrix. So if you consider from here, it follows that the gradient of J of x is equal to 2H transpose H. That's A. That's A. With me? Come on, guys. And how do you do that? I want you to do a simple homework problem. Ax, AB, BC, x1, x2. This is ax1 plus bx2. This is bx1 plus cx2. Are you with me? Compute the gradient of this. You get the solution. All of you, come on, guys. There's something you do, there's something I do. That's how we meet each other. So I want you to be able to do problems of simple types like this. So what is that I have? For JC to be minimum, I'm sorry, JX to be minimum, First condition, H transpose, HFX must be equal to H transpose Z. Second condition is H transpose, H is already symmetric, it must be an SPD matrix. This calls for solving an n by n system. And that's non-trivial. How many of you have solved a 3 by 3 simultaneous equation in your life? Good. You guys are brave people. How many of you have done 4 by 4 by hand? Hell with it. If you want me to compute the determinant of a 4 by 4 matrix, I will say I don't need the job. It's potential for committing errors, right? That's right. 2 by 2 is easy. But the idea carries over. And what are the methods for solving linear simultaneous equation? Kramer's rule. Method of Gaussian elimination. Are all with me, please? So simple. I'm not going to be able to do all of them in this class. But in a one semester course, we will do numerical methods for solving linear simultaneous equations of this type. And what are the methods? So linear system. There are two classes of methods for solving linear systems. One is called the direct method. Another is called iterative method. I'm talking about methods of solving this. That's non-trivial. The ultimate computational burden in data assimilation comes in at this stage. I have to compute the optimal solution. The optimal solution is obtained by solving a linear system if I use this approach. So what are the methods? The mother of all techniques in solving linear systems is Gaussian elimination. And that also goes by the name LU decomposition. LU decomposition. And this Gaussian elimination is for a general, A being a general matrix. But here, I don't have a general matrix, I have a symmetric partially definite matrix. Are you with me? In mathematics, the trick is you don't use the same tool to solve every problem. If the problem has a special structure, you have to refine your tool to be able to exploit the special structure of the problem. Are you with me? So you always use different tools to solve similar problems because the inherent characteristics of the problems are different. So if nothing else is known except that A is non-singular, I will use LU decomposition. But I know something more. A is symmetric. A is positive definite. Mathematicians, numerical analysts are extremely intelligent people. They give you, you tell me the property, I will give you a specialized algorithm for that. So to solve Ax is equal to B, A general, LU decomposition. A is symmetric, further specialization. A is symmetric and positive and further specialization. You give me more structure, I will give you more and more specialized structures. That's the beauty of algorithm development in numerical linear algebra. For every special character, you are going to have a specialized algorithm that exploits that property. So matrix books are filled with these specialized algorithms. So one of the specialized algorithms that we will use, that one could use to solve this linear symmetric partial system is called Cholesky decomposition. Cholesky decomposition, which is a special case of LU decomposition. There are further techniques in direct methods. It's called QR decomposition. It's called SVD decomposition. Are you with me? So there are several families of techniques. LU decomposition, Cholesky decomposition, QR decomposition, singular value decomposition. That's what SVD is all about. I want all of you to learn all these techniques. Why? Because Later, in different aspects of in data assimilation, they will invoke singular value decomposition. How many of you have heard of PCA, Principal Component Analysis? How many of you know PCA is essentially SVD? Only one. You derive PCA using SVD. SVD is a mother of many, many, many different algorithms. So this is most general, somewhat specialized, more specialized, more specialized. And SVD is applicable to many, many, many different problems. PCA is one of them. And if I want to compute the rank of a matrix, what's an algorithm? SVD is a good algorithm to compute the rank of a matrix. All of you? That's right. That's right. So we won't have time to go into the aspects of these algorithms. In a full one semester course, I cover each of these algorithms in my class. I used to. All of you? The story is not complete until you know many of these numerical techniques. That's why I tell you a good book on numerical analysis would be a good investment. With me? Good. What is the iterative technique? Iterative techniques. So what is the difference between direct technique and iterative technique? Direct techniques are like a black box. Are like a black box. You give Ax is equal to B, out comes the solution X. Something happens in here. Once you give control, you have to wait until it spits out the result. That's an algorithm to compute. Do this, and you get that thing. In the iterative technique, on the other hand, you always approximate. So you start with the initial solution X naught. You substitute X naught in Ax is equal to B. This is called the residual. If the residual is 0, you are done. Are you with me? If the residual is not 0, you compute x1 as a function. You compute x1 as a function of x naught and r of x naught, the residual. So using the error to correct a solution so that the solution moves towards when the error is 0. And that's the idea that was born in engineering in what's called feedback control. In the case of James Watt's engine. So what is the problem for James Watt? He invented the engine, but he wanted to be able to make the pressure, the steam pressure to be constant to get the thrust. So if you boil the water, the pressure increases. But the boiler has been designed only to hold up to certain pressure, otherwise it will explode. So I wanted to be able to maintain a constant pressure. So he invented a valve. If the pressure is high, pressure cooker. How many of you know cooking? You cook the dal for 5 whistles. So between each whistle, there is a time interval. Before the whistle blows off, there is a constant pressure. So you try to keep the dal in constant pressure at least for 10 minutes, five whistles, so that it can get cooked. So if the pressure releasing, that's an automatic mechanism. So there is a built-in, that is a desired pressure, the pressure is building. If the inside pressure is over the design pressure, release it. If it is less, the weight falls down. So the weight acts as a sensor. The weight measures the error between the maximum pressure and the current pressure. Are you with me, please? The temperature control in thermostat. Speed control of course, when you are driving in Bengaluru, you can never go in automatic speed, right? You need to have total control. But when on a highway, you put cruise control. So you set the speed at 80. If the speed is below, it throttles. If the speed is above, it brakes. All of it, me, please. Feedback control. You use the error to correct the situation. That idea came in engineering, James Watt's engine in 1800s. And that's an enduring and a fundamental principle that that pervades through all of engineering. And that's what we do. I want to control the error. I want to minimize the error. All of it, me, please? So some of the basic ideas has been around for a long time, but we give a shape to these ideas in a particular form. So what are the methods? I hope you all remember Jacobi method, Gauss-Seidel method, over-relaxation method, over-relaxation methods. So you can solve the system by one of several algorithms. Direct techniques, iterative techniques. Direct technique is a black box. Most of the direct techniques, the time complexity is the order of n cube. What does it mean? To be able to solve an n by n system, the amount of work that you need to do increases by the third power of the size of the problem. So if you double the size of the problem, the cost increases by 2 to the power of 3, 8 times. You talk about large-scale problems. That's one of the challenges. All of you? That relates to what's called the time complexity involved in solving problems. If you use a direct technique, once you give control, you have to wait until the computation stops by itself. But in the case of iterative techniques, you have the control. You can, in finite precision arithmetic, you can never compute anything exactly. I hope you all remember that. Everything we do is approximate. So what is one of the advantages of iterative technique? I have total control when to stop. If two solutions differ in second decimal, it's okay. If two solutions differ in fifth decimal, that's okay for some. If two solutions differ in eighth decimal, that's okay for somebody else. Understand? So depending on the accuracy that you are dealing with. So what accuracy you should be looking for? Let's talk about that for a moment now. You have data, right? You can never measure data accurately, even though I am assuming I have a means of measuring data accurately. So your solution need not be more accurate than the errors in the data. Are you with me, please? If you are looking for, if your errors in the data is up to first decimal, there's no point in seeking a solution correct up to 8 decimals. That begs the question. So what kind of accuracy you need depends on what kind of errors have gone on into the input data that give into the algorithm. All of you with me? Direct technique, iterative technique. There are books written only on iterative techniques alone. There are books written on direct techniques alone. When I talk about books, these are 500, 400-page long books. Are you with me? Who are the beneficiaries? Data assimilation folks are the beneficiaries. And these have been very nicely, beautifully coded in MATLAB. So if you have access to MATLAB or Python library, please check what kind of libraries you have to solve a variety of linear systems and take notes of all those.
Did your data assimilation book contains all these basics?
Data assimilation book?
The data assimilation book that you have written.
We talk about all these things. That's right.
But yesterday I looked into the book, but I didn't find it.
There are chapters. Show me the book, I will tell you. Not now. No, don't challenge me right now. I'll show it to you. We have one chapter on matrix methods. I think it's chapter 8, chapter 9. And one chapter on optimization technique is sequential optimization. Are you with me? We wanted to make our book as complete as possible. So we have chapters on any and every topic. There are 32 chapters. So we have it, sir. You didn't probably look at the right place. Thank you. Are you all with me? We deal with the direct technique. We don't deal with the iterative technique in our book. So what, are all of you with me now? Good. So are we good to go on solving this problem? Can you find the optimal solution by solving that? So mathematically, I can write the optimal solution to be either x star I least squares, which is equal to H transpose H inverse H transpose Z. So mathematically, there is an expression for the optimal value. How many of you are with me? Come on, guys. You all look a little tired. I hope you all had a coffee. Coffee or tea perks you up, right? That's right. So mathematically, I can write this, but I have to sweat hard to get this x star computationally by invoking to either this class or that class. Are you with me? That's right. For the 2x2 system, you can do by hand. That's a homework for you. Please do. Please do. Now, before I go further, I have an obligation to show that this must be true in order to claim that this is minimum. Are you with me? Mathematics keeps your feet to the fire. Mathematics is not going to let you quickly. You have to answer all the questions. So what is the last question we need to answer? The matrix H transpose H, which is the matrix of this system, must be non-singular. I said it's positive definite. Positive definite matrices by definition are non-singular. So if positive definiteness implies non-singularity, then I have earned the right to write the inverse. So this is the mathematical formula for my optimal solution. All of you? So I have the burden to show that I already showed you this is symmetric. I want to show this is positive definite. And that's what I'm going to spend a few minutes on. All of you? You all know where we are right now? I don't want you to be lost. Good. Okay. Now let's, I want to keep this. So let's come in here now. So, H transpose H is symmetric. So consider the quadratic form. Hey, that's a term, that's the quadratic form in the objective function right here. So what is quadratic form geometrically means? You see the parabola? Parabola is a quadratic form in 1D, ax squared. What is a parabola in 2D? You take the 1D parabola, rotate. It becomes a bow. What is a parabola in multi-dimension? X transpose AX. A parabola has always a unique minimum. So in order to show that this is the parabola, I have to show this is positive definite. To show that is a positive definite, I'm going to rewrite this as this is X transpose H transpose H of X. You remember the matrix product is associative. Matrix product is not commutative. What is the difference between commutativity and associativity? Associativity tells you I can group them any way I want. You remember the example of you shopping 15 items? When the clerk adds it, you don't care what order the clerk adds it. So long as the entry is right, the addition should be, the sum should be constant. Are you all with me? So associativity, commutativity. So using associativity, I can write like this. This I can also write H of X transpose. So look at this now. H of X is a vector. H of X is a vector. So what does it look like? X transpose X, Y transpose Y. What is this? This is equal to the norm of H of X. All of you? Sometimes some people, when they see the norm symbol, they say, oh gosh, it gets very difficult, right? That's right. But it's very easy to be able to understand if you approach it appropriately. Okay, what is that we know? The norm is always non-negative. Norm is positive when the vector is non-zero. Norm is zero only when the vector is zero. You remember that? The definition of a norm we saw last class. So this will always be greater than 0 if h of x is not 0. All of you with me? So what does it now comes to? The whole question of the existence of minima of this rests on this fundamental property, namely h of x not being 0 for any x. All of you? Are you all with me now? Now I'm going to go to vector space theory. So what is h of x? That's what we did vector space theory last class. So h of x, you remember a matrix can be partitioned either row-wise or column-wise. I'm going to partition this matrix H column-wise. So this is H star 1, H star 2, H star n, x1, x2, xn. Please understand, H star j refers to jth column. H I star refers to ith row. That's a standard notation. So what is this? This is essentially H star 1 x1 plus H star 2 x2 plus H star n xn. What is this? This is a vector constant. Say scalar, vector scalar. Now do you see this is linear combinations of the columns of H? Hello? When is a linear combination of the columns of H can never be 0? That's a condition. So in order that this is not 0, I need to be able to establish that the linear combinations of the columns of H can never vanish for any x. H's are fixed, any x. That can happen only when the columns are linearly independent. Hello? You all have an aha here? Yesterday when we said linear independent, dependent, oh gosh, once more. How many times in my life I have to hear commutativity, associativity, linear independence, I never use them. You better believe we use it here. The existence of solution rests on the columns of H being linearly independent. And who makes H? H is called the design matrix. So let's talk about that now. So in my problem, what is my problem? My problem is Z is equal to H of X. In the case of a particle moving in a straight line, what was H? H is a m by 2. The columns were designed by me, designed by you. So H is the bridge between model space and the observation space. You remember that building, the 2 blocks. So H is called the design matrix. So when do you say a problem is well designed? If and only if H is a full rank. And a data assimilation problem of this type is a well-designed problem if H is such that the columns of H are linearly independent. And just to remind you, how do you measure linear independence? The angle between any pair of vectors must be non-zero. No vector should lie in the subspace designed by the other vectors. Are you with me? That's right. Those are the conditions. So it is whose responsibility? So if your problem is screwed up, who screws it up? You. Don't blame anybody. So in mathematics, we talk about 2 classes of problem, well-posed problem and an ill-posed problem. A problem is said to be well posed if the design matrices, the columns of the design matrix are linearly independent. If the columns of matrix H are not linearly independent, that leads to what is called collinearity. Where does the linear independence, when do you lose linear independence? When there are collinearity between vectors. So an ill-posed problem arises largely because the columns of H has some collinearity issue. When they are collinear, the columns are linearly dependent. If the columns are linearly dependent, I can find a set of coefficient using which I can annihilate this. So h of x will be 0 for some x not 0. Everybody with me, please. That means the problem is ill-posed. This cannot happen for all x. Ill-posed, well-posed, linear dependence. There's another terminology in matrix theory now I'm going to use to describe the well-posedness and ill-posedness. How many of you know the concept of a rank of a matrix? Raise your hands, guys. Keep your hands raised. Let others see. Those of you who did not raise the hand, why? I want you to think about this. Rank of a matrix. How do you define a rank of a matrix? A matrix can have two types of rank, column rank and the row rank. The rank of a matrix is equal to the number of linearly independent columns. That's called a column rank. The number of linearly independent rows is called the row rank. For any given matrix, the row rank must be equal to the column rank. When the mathematics professor proves this in the linear algebra class, everybody gets bored. He said, well, let him have it. I'm not worried about it. You need it now. Are you with me? That's right. So now I'm going to combine the concept of a rank with the linear independence. Now you see why I did not do linear algebra by itself? Because if I did by itself, you have already heard linear algebra in your life twice, right? Come on, guys. Third time's no charm. But if you do in the context of an application, it will stick someplace. So I'm now going to talk about the concept of a rank of a matrix and relate it to ill-posed and well-posed. Can I erase this part? Yes. So I'm not going to write all of them. Rank of A. So if A is a n by n matrix, rank of A is less than or equal to n, is always greater than or equal to 0. What is the matrix for the rank of 0? 0 matrix. When A is non-zero, is always satisfies the inequality. So when the rank of A is when the rank of A is equal to n, we say A is full rank. Else it is called rank deficient. So linear independence relate to full rank. Linear dependence relate to rank deficiency. So now let's combine the two. When is H transpose H symmetric and partially definite? When H is a full rank matrix. But before I do that, I want to extend this to rectangular matrices. Let H be m by n. The rank of H, the rank of H is always less than or equal to the minimum of m and n. Are you with me? If it is equal to the minimum, that implies A is full rank, H is full rank. H is full rank. These are the definitions from linear algebra. So it should bother you. Given a matrix, how do I compute the rank of a matrix? That's a computational problem. You cannot say, let the linear algebra people take care. Because in data assimilation, you need to worry about this. So in the margin of your notebook, please write a question to yourself, how to determine the rank of a matrix. What is an algorithm for that? One algorithm is SVD. One algorithm is SVD. So in our problem, I have H. H is the m by n matrix. So what is that? I have already tacitly assumed H is a m by n matrix where m is greater than n. M is greater than n. I have more observations than the number of parameters to be estimated. I'll go back to the example that you do in basic physics problem. Acceleration due to gravity g is one constant. How many times do you repeat the experiment? Length L1 times T1, length L2 times T2, length L3 times T3, length L5 times T5. You repeat the experiment multiple times to be able to determine. So even though there is one parameter, you collect a lot more data. If the amount of data is larger than the number of parameters you estimated, that is called over-determined problem. With me? So if you are setting up an experiment, if you have set up the experiment, repeating the experiment is less expensive. So in situation where the cost of conducting the experiment is very low, you can afford to generate more data than the number of unknowns. On the other hand, if the cost of conducting the experiment is very large, you may not afford to do experiments many times. I'll give an example. Suppose they say in this mountain there is gold. Everybody likes gold, right? That's right. Gold is good as gold. So I want to be able to excavate. So before I start excavating, borrowing money from the bank to be able to start an excavation company, I need to be able to estimate how many tons of pure gold are hidden in this mountain. I need to estimate it, right? Are you with me? That's a data assimilation problem, guys. How much rain is in that rain cloud? How much gold is there in that mountain? How much petrol is hidden below the earth? Are you all with me? All these problems mathematically are similar. You use radar to be able to estimate the amount of rain in the cloud. You use satellite to be able to estimate the temperature of the sea surface. So how do you estimate the amount of gold in the mountain? To drill one hole, it costs $5 million. Even the richest company cannot afford to drill more than probably 15 holes, because there is really money down the drain. Are you with me? So the cost of conducting the experiment in excavation for the gold, for the silver, any mineral, all of it may. Come on, guys. It's very expensive. So I do need to do the estimation problem with less data. That's called under-determined problem. When you have radar, satellite, radar costs you about $300 million. Satellite costs you $250 million. But once you put a radar or a satellite, they are going to live for 50 years. They are going to generate data 24/7. They spits data, large data. That's what my friend was talking about yesterday. So most of the problems in meteorology, meteorological related situation where you use data from satellites, LiDARs, in situ measurements are much rarer. Satellite data is plenty. So many of the problems in meteorology are over-determined problems. Many of the problems in geophysical exploration are under-determined problems. All of it may please? In today's class, I'm only talking about m greater than n over-determined problem, more data than the number of parameters on hand. So in this case, m is greater than n. When m is greater than n, the minimum of m and n is n. For this matrix H to be full rank, the rank must be n. If the n columns of H are linearly independent, rank of H is n. H is a full rank matrix. So what is the conclusion? All my theory holds good, provided my matrix H is a full rank matrix. Done. You all have an aha here? Come on, guys. Your silence is deafening. Say aha. Come on, guys.
Wow.
That's right. Why are you shy to say aha? That's right. When you enjoy something, the aha, wow should come naturally, guys. You should never hide your emotions. That's what psychologists tell you, right? If you want to cry, cry it over. If you want to laugh, laugh it over. In a class, enjoy. Have you seen the Coke commercial? I watch TV more for the commercial than for the shows. The people who create the commercials are the most intelligent people in the world. Look at what the problem they have to solve. They are given 30 seconds. They have to sell a product. Are you with me? They have to do in 30 seconds a picture, a jingle, this, that, and so on. It registers in your mind. So when you go shopping to the mall next day, hey, I saw it, I want to get it. Are you with me? That's right. So there's a famous Coke commercial. A bear will come. He said, I'm thirsty, I'm thirsty, I'm thirsty. Somebody will give the Coke can to him. He will open it and drink. He'll take the first sip. That's a bear telling. That's aha for humans, right? Come on, guys. And then what the commercial will say at the end, at the end, enjoy the moment. You got that idea now? There are only two things. There is no sound. The bear will come, he will say, I'm thirsty. Somebody will hand the Coke can to him, and the bear will open it. He will take a sip, he will say, and then the commercial will say, enjoy the moment. You never forget it. So what is the theme here? Not the Coke, not the bear, but enjoying the moment. That's the message. Are you all with me? Are we done? One half of the static deterministic problem, we are done. What is the second half? What is the theory when m is less than n? It turns out there is no relation between these two problems. These two problems have totally different character, at least mathematically. That's what we will move into. But before we go there, I want to quickly summarize how we got here. I expressed a physical problem. We built a model based on physics. I arranged matters to collect observation. In my original problem, I had two unknown parameters, the initial position and velocity. I have m observation, more observation than the data. We formulated it as a linear least square problem. The problem was reduced to one of minimizing a quadratic objective function. The quadratic objective function must take a bowl shape, but a bowl naturally has a minimum, unique minimum. So here comes the problem. Suppose you concoct a cost function, it doesn't have a unique minimum, multiple minimum. Are you with me now? That's called multimodal problem. So I'm going to talk about the varieties of problems. Are we done with this? So let me. I want to talk about all the varieties of optimization problems. Before I go there, I want to, one of my favorite things is to talk to you about the things. Why do you come for short courses? I'm going to tell you what should be your goal. So in life, there are known There are unknowns. There are knowns. There are unknowns. You should know what you know, right? People said, yeah, I have heard it, but I forgot it, right? You should know what you know, what you are supposed to know. Known is known. What is known unknown? I don't know whether how life will be on Mars. I want to know more about it. I don't know now. Are you with me? I want to know, this is unknown. I want to know more about it. So what is learning? What propels you to learn? The known unknowns. Are you with me? That's right. I don't know how Tibetan cuisine is going to taste, so I'm going to go to a Tibetan restaurant this evening to taste Tibetan food. Known unknown. Okay. Unknown known, that's an oxymoron. What is unknown unknown? I don't even know what I don't know. Are you with me? So an unknown unknown becomes a known unknown, becomes a known known. So what is the learning process for me? The learning process for me comes from so why are you here? To some of you, maybe it is unknown unknown. They are sending me to Bangalore. Bangalore is a great city. Everything is paid for. Let's go. That's one of the goals. What's the second goal? I want to finish my PhD. My advisor says you need to learn data assimilation, right? I know data assimilation is needed, but I don't know what are the components of data assimilation. So it was probably unknown unknown. So what do I make you? I make you from unknown unknown to the known unknown. Maybe some known known. So what is going to drive you? You go for seminars to know what is that you didn't know. Now you know what you need to know and knowing it. All of you with me? Come on, guys. So at the end of the 15 days, you are going to be here. You have to compare your state when you came and when you're out. If they are the same, we did not cause any problem. We did not cause any change in you. I hope it does that. You remember the Bayesian we talked about? The prior, experience, posterior. That's exactly the model. So the learning model is essentially Bayesian. The unknown unknown becomes a known unknown that becomes a known known. I would like you to look at these things from this perspective to be able to say, yeah, I know this, I know this, I know this, I don't know this, I want to know this, so on and so forth. Good. So let's talk about the classification problems now. So the static deterministic problem, there are two things. M is greater than unknown, Z is equal to H of X, and M is less than N. This is overdetermined, this is underdetermined. And the solution for this is X. And that's what we work towards today under the assumption H is full rank. So if you don't get the good solution, don't blame anybody, blame yourself. Not to blame yourself, that helps you to decode, that helps you to make the problem right. You have to convert an ill-posed problem to a well-posed problem. I screwed up in my experiments. So this is what we are going to see in the afternoon, maybe after some time. Then we come to optimization problem. The optimization problem is uni-objective versus multi-objective. Objective. Unimodal multimodal. So what is unimodal? The example of a unimodal algorithm is a parabola. What is multimodal? So I have this minimum and this minimum. What is uni-objective, multi-objective? We already talked about it. Every engineering design is multi-objective. So engineers have a much harder problem than problems in meteorology. Are you with me? So what is the only goal? Reduce the forecast error. You make your prediction more reliable. Unimodal, multimodal. So we are talking about uni-objective, unimodal. All of you? So how do you guarantee my problem has one mode? By designing the objective function appropriately. In the language of optimization theory, we want to make the function what's called convex function. I'm not going to go into that, but if you see the word convex functions are models for unimodal function. What is an example of a convex function? Parabola. Parabola. All of you? So why am I telling this? If you thought your problem is difficult, think of the guys who work on this and on this. Are you with me? There are many people in engineering, they work on that. Building a house doesn't have a unique solution. Building a car doesn't have a unique solution. Building a blender that you use in your kitchen doesn't have a unique solution. Building a fan doesn't have a unique solution. Are you with me? That's right. So engineers deal with every day. Engineers deal with it every day. Uni-objective, multi-objective, unimodal, multimodal. So we talked about over-determined problem. Formulate as a uni-objective problem, formulate as a unimodal problem, and solve that. All of it, me? Good. Any questions? If there are no questions, I'm going to switch over to underdetermined system. I want you to understand the difference between over-determined and underdetermined in a very fundamental way. With me? So I'm going to work with a very simple example to tell you the difference. So there are three cases. M can be equal to n, M can be greater than n, M can be less than n. With me? Good, let's do that. Before I jump in, are there any questions? If M is large, we call it large data problem. If n is large, we call it large data problem. So a problem can be large because the number of parameters is large. I have a friend who works in the Institute of Science. Dr. Maitli knows him very well. They have a climate model where there are 69 parameters in the model. It's a collection of partial differential equation with 69 parameters. How do you estimate 69 parameters for a climate model where the model has to run not for 1 year, 2 years, but 100 years, 200 years, 500 years? Are you with me? Those are truly large-scale problems. Those are truly large-scale problems. With me? That's right. Good. So now let's try to understand the fundamental difference between there are books written on multi-objective functions. Please, you all Google very well, right? Come on, guys. Go to Wikipedia, find out algorithms for multi-objective optimization, algorithms for multimodal problems. Are you with me? So, good. So let's try to say m is 3, n is 2. 5x1 plus 7x2 is equal to 19. 3x1 minus 17x2 is equal to 11. 11x, oh, I kept the same number, plus 5x2, I had 5. 9x2 is equal to 19. Oh, not 19, 21. That's for the fun of it. 3 equations and 2 unknowns. As opposed to so what is this? 9x1 plus 10x2 plus 11 x3 is equal to 9. 2, 15x1 plus 7x2 minus 5 minus 5 x3 is equal to 7. So when you formulate the problem, your z is equal to h of x. Must either look like this or must look like this. As an example. Everybody? Come on, guys. So let's do this. So how do you solve this? I know how to solve 2 equations and 2 unknowns, provided the system is non-singular. So 5 times 17 minus 7 times 3 is not 0. So that matrix 2 by 2 matrix is non-singular. I can solve for x1 and x2 from these 2. So if I solve these 2 equations for x1 and x2, should that satisfy the third equation? Huh? Ah, that's why may or may not be. In general, it won't. Why? If I did not participate in the solution process, you cannot expect me to participate in your game. In trying to find the solution x1, x2, when you use 2 equations, you did not consult the third equation. If you did not consult the third equation, you cannot make him responsible to solve for the same solution for the first 2. So he'll say, I'm independent. You went your way, you did not even talk to me. You are not going to satisfy me. So what does it tell you? In general, when you have 3 equations, 2 unknowns, there is no solution that satisfies all the 3. Under what condition there will be a solution? So let's consider 2 cases now. So z is equal to h of x. Z is equal to h of x. Are you with me? So if z must be given z and h, there must be a solution x. Means what? Z must be expressible as a linear combination with the columns of h. You remember the span of h I talked about yesterday? A span of a matrix is equivalent to the space spanned by the columns of h. Are you all with me? Come on, guys. So if the vector z happens to lie in the span of the columns of h, then there exists an x such for which z will be equal to h of x. So x exists if and only if z belongs to span of h is a shortened version for the space spanned by the columns of h. You remember my friend said may or may not. When there is a may there may be a solution when the span condition holds good. But if it does not hold good, then there is no solution. If there is no solution, this system is called an inconsistent system. Inconsistent means what? There exists no x for which all the 3 equations can be simultaneously be true. All of it me? So now I'm going to tell you the concept of a solution. What is solution in mathematics? Left-hand side must be equal to the right-hand side. Therefore, when there is no solution means what? I can never find an x for which z is equal to h of x. It's true. All of it me, please? In an inconsistent system, there is no x for which z can be made equal to h of x. In that case, what do? You compute E of x is equal to z minus h of x. So what is this? This is a vector of size m. If there were to be an x for which there is a solution, E will be a zero vector. So in an inconsistent system, the error vector is the m vector, which in general will not be zero. If the vector is not zero means what? What is the next best thing I am willing to settle? I want to make the length of the vector as small as possible. All of you with me? Hey, that's life, right? I would like to have a car and a house, but I have 2 kids. College is expensive. They are knocking on the door to go to college. Are you with me? So I don't want to have a car. I will go for a 2x2 two-wheeler. Life is full of compromise, right? I would like to do this, but because of this, I would like to do this. I would like to do this because of this, I'm doing this. If you think for a moment, if you have all the wealth in the world, your life will be miserable because you have nothing to work for. Thank goodness we don't belong to that category. At least I can talk for myself. All of you? That's right. The joy of being able to work for something. Okay, so let's come in here now. So solution means E of x must be 0. If there is no solution means I would like to find an x for which E of x will have a shortest length. What is the shortest length means? What? I want to be able to minimize the square of the norm of that with respect to x. And that's the least square problem. So what is the least square problem? Least square problem is an extension of the solution techniques to solve problems for which there is no solution in the regular sense of the word solution. So when I say least square solution, the least square solution is not in the sense of the word solution, left-hand side is equal to the right-hand side. The difference between the left-hand side and the right-hand side in some measure is minimized. Now, do you see the relation between least square solution and a solution? We always, mathematicians are very clever people. If I can't have this, I will have this. If I can't have this, I will have this. If I can't have this, I will have this. They will give you not one solution, but a frame of solutions. So when you are doing algebra, you always look for a solution, the solution. Now you are looking for the solution, which is the least square solution. Hey, this is a standard question in oral exam. Tell me the difference between the least square solution and the solution. I have done data assimilation, but I don't know, right? That's right. Are you with me? That's right. So the reason why we settle for minimizing the sum of the squared errors is because we cannot get the error to be 0, because there is no x for which the left-hand side may be equal to the right-hand side. And that's a property of overdetermined system. So only in a very rare case, my z will belong to the span of H. H, please remember why that will not happen. H, this is the model space. This is the observation space. This is x, this is z, this is H. The guy who measures the observation, he doesn't care how you build your H. Are you with me? Are you all with me, please? There is no relation between Z and H in an explicit sense. Therefore, the properties of H need not worry about whether Z belongs to the span of H. Are you with me? That's right. Therefore, more often than not, the problem is inconsistent. Least squared method is a method for solving problems for which there is no solution in the regular sense of the word solution. So the least square solution is an extension of the concept of solution. The entire data assimilation rests on least square method. Are you with me? Come on, guys. Well, you may say, hey, there are Bayesian techniques, there is this technique, there is this technique. They're all variations of the same idea. Similar ideas. Are you with me? Are we done with the overdetermined system? Why we did least squares? What is least squares? How is it different from the regular method of solving linear systems? Are you all with me, please? I also want to tell you one more little thing. I want to be able to solve z is equal to h of x, but what is this equation? This equation simply looks like multiply this by h transpose, multiply this by h transpose. Whoa, I got this. You may ask a question, why didn't you do that? Why did you work hard for this long? If I simply multiply this, that's a trickery. There is no mathematical basis. After doing all the hard work, we now look at, gee, it looks as though you give me the original solution, I'll multiply both sides by h transpose, I get the necessary condition for the minimum. Are you with me? That's right. It's an after fact. It's an after fact. Everything needs to be proved. Everything needs to be performance guaranteed. That's the idea. Good. Now let's turn to the underdetermined system. In the case of underdetermined system, yeah, I already have the system here. In the United States, there is a saying, you need to know where the rubber meets the road. The car tire meets the surface, right? When the plane lands, that's where the heat is generated. So I want to know where the rubber meets the road. That means I want to know the crux of the problem. So I'm talking about some of the fundamental, enduring discussions about least squares on which the entire edifice of data assimilation is built. All of you? That's right. Good. Now let's look at this now. So what is it I could do? I could get this to this side, 11x3. I could get to this side, 5x3. I had 3 equations and 2 unknowns. I kicked one of the variables to the right-hand side. I got 2 equations and 2 unknowns. Assuming the determinant is not 0, it is not. I can solve for x1, x2. Whichever method you solve, the solution x1, the solution x2 is going to be a function of x3 because the right-hand side is a function of x3. All of you? How many possible values of x3 are there? Infinitely many. There are infinitely many solutions. Uh-oh. In one case, there is no solution. In the other case, there are infinitely many solutions. Under what condition there is a unique solution? When m is n, when m is equal to n and h is non-singular, then there is only one solution. So the square system lies in the middle. Overdetermined system, underdetermined system. In the square system, if the matrix is non-singular, there's a unique solution. In the overdetermined system, there is no solution. In the underdetermined system, there is infinitely many. When it pours, when it rains, it pours. Are you with me? That's right. Now, do you see the difference between overdetermined and underdetermined? So you now know what geologists have to deal with. In geology, conducting experiments means collecting data is very expensive. All of you? All the batteries we do, they use rare metal. There are only few places in the world they can find these rare metals. It is told that at the bottom of the Indian Ocean is very vast, it's ours. It goes thousands of miles south of Kanyakumari. There is a lab in Madras, Chennai. They talk about ocean technology. There I visited that lab. They have robots they make that can go 3 miles deep, scoop up and bring it up. And they analyze for the presence of rare metals. All of you? That's right. So to turn the robot 3 miles deep and get it out, very expensive. So many of the geophysical explorations, you have to determine the solution when there is very little data. So what's my question? Meteorologists don't complain if you have more data. The other problem is even more challenging. All of you? You just have to deal with each of the problems. So we are not the only one who is solving data assimilation problem. Every geology problem is related to data assimilation. Every atmospheric science, oceanography problem related to data science. Now, do you see the difference between all the three problems, please? That's right, static problem. So now, what is the challenge? How do I solve the problem where there are infinitely many solutions? What is an optimal solution? How do you formulate the problem? What is the minimization problem? Now, please understand, if there are millions of solutions, the E is equal to Z minus H of X is 0 because there are infinitely many X. So E transpose E is 0 transpose 0 is 0. So the old methodology will not cut. All of it me? Come on, guys. I have to develop a new pathway to thinking. I have to develop a new pathway to thinking. So what is the corresponding optimization problem? How do I formulate that problem? What are solution methodologies for that? That's what we will do after lunch break, 2:30. But before we break, we still have about 10 minutes. I'm going to talk about one problem that I have not talked about in the context of overdetermined problem. That is as follows. Are you with me? So before I go there, are there any questions on these things? 3 equations, 2 unknown, 2 equations, 3 unknowns. Very simple ideas, but every idea is hidden there. You want to be able to express your problem in the simplest possible way. What is the difficulty? You see it here, you see it here, you see it here. With me? Good. Now let's do one more to complete the story. So, in the case of m greater than n, E of x, my J of x is equal to E transpose x E of x, which is equal to Z minus H of x transpose Z minus H of x. And this is a quadratic function. Are you with me? How many of you remember that? That's right. So how does it look like? In general, it looks like x transpose AX minus B transpose X plus C. What is A? H transpose H. What is, let me put a 2 here. What is B? B is H transpose Z. What is the letter C? Z transpose Z. You remember that? Come on, guys. We had all the three, right here. I have not, right here. This is X transpose AX. This is B transpose X. That is C. That's a quadratic function. So how did we solve the problem? One way to solve the problem is set the gradient of j of x equal to 0 and solve the resulting linear equation by a direct method, by iterative method. Are you with me? What is the other technique? The other technique is called sequential minimization. What is the sequential minimization? Sequential minimization is a technique mountaineers, they want to climb every mountain in the world. I have friends who say, I have only 2 more mountains to climb in the United States. That's their hobby. They spend a lot of their money to travel to the places, stay there for 15 days, climb the mountain, break a leg or 2, come back, get cured, go back to the other mountain. The drive that I can climb. So let's talk about hill climbing. What do? On a given day, I can only trek for 6 hours because you have to take a lot of things in your hand. So you are starting at a base station. You look at the mountains. You know where the peak is. You cannot go by the Euclidean distance, fly. You have to trek. You have to do an L1 minimization. I want to be able to walk the shortest path. At the end of the given day, after 6 hours, I want to increase my elevation by the maximum amount. If I keep increasing my elevation by the maximum amount, sooner or later, I should reach the mountain. So what do good mountaineers do? They have a base station, they put a tent, they have coffee, whatever they want to do. They take rest, early morning, they get up, they already have planned. I want to be able to trek this many miles in this direction to get there. You may not be able to go directly. So what is the direction they have to pick? Which direction, if I walked for 6 hours today, I will increase my elevation? Do you see the question? So all the maximization algorithm in computer science and applied mathematics are borrowed from the algorithms what humans use to climb hills. That's why they are called hill climbing algorithms. The opposite of hill climbing is minimization. The minimization and maximization are the same problem except for the sign of the cost function. Minimum of f of x is maximum of minus f of x. Are you with me, please? How many of you are with me? That's right. So that algorithm is called gradient algorithm. Why gradient? Gradient mathematically represents the direction of maximum rate of change. That's a theorem in calculus. All of you? So if I want to be able to increase my altitude, moving towards my things, I need to move in the direction where my rate of increase is maximum. So what is the opposite of gradient? Negative of the gradient. If in the minimization problem, what is that I need to do? I need to be able to go down the hill where I will get the maximum rate of decrease. That is me. So I have one base station today, xk. I want to get to the next base station. This I'm going to go for the minimization algorithm by alpha k times delta j of xk. This is the gradient of the objective function at my current position. The negative of the gradient tells you the maximum rate of decrease. I cannot keep going in that direction. I will miss my minimum. So I want to go in the direction. So this is the vector times a scalar. That's a vector. Vector minus vector, scalar times the vector, that's a new vector. So the new base station is equal to the old base station minus, yes, step length. So this is called the step length. How far do I go in this direction? So, the sequential minimization, there are only three key things. Where am I? Which direction I need to go? How far I go in that direction. Where am I is xk. Which direction to go? Negative of the gradient. How far you go? Alpha k. Why alpha k? I cannot keep alpha fixed. If alpha is fixed means what? That's a fixed length. You should not fix. Some days I may be able to grow longer. Some days I may not be able to go that long. So the amount of distance you are going to cover must depend on the situation, the terrain. If there is a huge rock in front of me, I don't want to go and hit with the rock. I want to go to the sides. If there is no rock, boom, I can climb. So alpha, depending on k, is called adaptive. So this is sequential adaptive gradient method for seeking the minima. So either you solve the linear system by direct method or iterative methods. This is called sequential minimization technique. These are the two classes of techniques. In our book, we have described all of these algorithms. Matrix methods, direct method, sequential method. There are three classes of algorithm we talk about: gradient method, conjugate gradient method, quasi-Newton method. Are you with me? I want you to hear all these things so that you know what they are. Gradient method, conjugate gradient method, quasi-Newton method, I'm sure every one of you in numerical analysis must have heard of Newton-Raphson technique. How do you find the zeros of nonlinear function? F of x is a nonlinear function. I want to solve for f of x is equal to 0. Are you with me? So I would like to suggest to each of you, please, you should promise yourself, for your own self, before the end of the summer, I will have one book on each of these categories in my personal library. One book on optimization, one book on probability theory, one book on statistics, one book on linear algebra, one book on multivariate calculus. Come on, guys. Each book is less expensive than a pizza. Are you with me? Come on, guys.
Can you recommend, sir?
What that?
Can you recommend the book names?
There are only probably 1,000 books on linear algebra.
That is why I am asking. If I will search in the Google.
No, certain things you should make decisions on your own. You shouldn't buy because I said it. Most of the good linear algebra books are good. Most of the optimization books are good. Okay, you look at the references to my book. Okay, we give references to that. So what's the best way would be to grab a book like ours, read through, then I want more of it, go to the references, there are books, go there. Or easiest way you all know how to do, Google. Are you with me? I don't have to tell you that. You do it anyway, right? That's right. For everything you do Google, right? That's right. Your knowledge is essential. Okay, I want to ask you a question. When was the last time any one of you went to the library? And what time was it? Do you have a library in the place where you work? Why didn't you go? When was the last time you borrowed a book? How do you read news? How do you read research papers? How many of you print a research paper? Good. You need to print a research paper and write your comments. I don't know this. I know this. I don't know this. I don't know this. I knew this. You got to do that. Are you with me? Please, printed books are good. So that's a good place to go. If you go for a Google search, the first 5-10 books that comes up, they're generally very good books. Okay? So we will stop right now. Please take over.
So we'll break now after lunch, 2:30.